All right, so this is the second lesson in our probability distributions unit. We are looking at binomial distributions. First of all, a definition for us. This is Bernoulli trials. And what these are is repeated independent trials. Remember, independent means that one trial does not depend on what happened in previous trials. So for example, rolling a dice, the dice doesn't pay attention to what has happened in the past and try and do something different. Okay, so these are independent trials. They are also measured in terms of something happening or not happening. So if it happens, it's defined as being a success. And this doesn't always have to be a good thing. So for example, if we are looking at how many defective products we get, a defective product could be considered a success. Okay? So we're just looking at something happens or it doesn't happen. So first of all, let's look at flipping a coin 3 times. All right, we are interested in the number of heads we get when we flip a coin 3 times. So I can create the probability distribution using my tree diagram. I can count up how many times I get 0 heads, how many times I get 1 head, 2 heads, and 3 heads, and create these probabilities. Okay, so in this case, flipping a coin for a specific result is considered a Bernoulli trial, where getting a head is a success and tails is considered a failure. So if I were to expand this, flipping a coin 5 times, and if I want to find the probability of heads 5 times, or getting heads 3 times, or getting heads 2 times or less, well, this is a pretty big tree diagram. On the right here, you can just see half of the tree diagram, okay? So what if I wanted to flip a coin 10 times? I don't even want to think about drawing that tree out. It would be massive, all right? So there is a solution to this problem. It is called a binomial probability distribution, and it's going to make calculating these things a little bit easier. So the characteristics of the binomial distribution, we are using Bernoulli trials. So all trials are independent. The outcome of one trial doesn't affect the probabilities of any of the later trials. The probabilities of success is the same in every trial. That's part of being independent, okay? The probability of rolling a 2 on a die is 1 in 6 every single time I roll it, all right? There's only 2 possible outcomes. Either I get a 2 or I don't get a 2, all right? So I'm not concerned with each of the different results on the die, only the one I'm looking for or not happening, all right? So my random variable called x is the number of successes in a given number of trials. So I'm not just rolling the die necessarily once. I might be rolling that die 5 times, and I want to know how many 2s I get in all of those rolls. So the probability of getting x successes, we're going to use this formula. P of x is the probability of getting that many successes. Okay, so this is not a multiplication again. This is part of my notation, part of my formula. So P of x is equal to n choose x. So we have the number of trials, choose the number of successes I want. P is the probability of a success on any one trial. So again, if I'm rolling 2s, this would be 1 out of 6 to the power of how many 2s I want, times Q. Well, Q is the probability of a failure. So it's 1 minus P. So in this case, it's every other roll on that die, or 5/6. And I need how many of those other things. So if I want 2 2s in 5 rolls, then this exponent would be 3. It would be my 3 other rolls. So to go back to our 5 flips of a single coin, how many heads do I get? And I want to calculate, remember it's a distribution, so I'm going to calculate all the different outcomes. I get 0 heads or 1 head or 2 heads and continue. I'm going to use this formula. So P, the probability of getting a single head, would be 1/2. Q is the probability of getting anything but heads, in other words, tails in this case, so also 1/2. N is my total number of trials, so it's 5 flips. And X is each individual probability distribution the number of heads I want. So X is going to change for my whole probability distribution. So here we are. We can see I've got my values filled in, half, half, 5, and X ranges from 0 through to 5. And then we can put it in a chart form. X is my first column, 0 to 5. Here's my calculation, 5 choose 0, times a half to the power of 0 for 0 heads, times a half to the power of 5 for all my tails. And then as a decimal, you can see all these probabilities. And notice when I add up all these probabilities, I should get a sum of 1. All right, we can also look at the expected number of successes. So the expected number of successes for a binomial probability distribution is simply n times p, the number of trials times the probability of a success in any one trial. So if I'm flipping heads 5 times, or 5 coins rather, I'm going to go 5 times. 1/2 is the probability of doing heads. If I want 6 rolls of a single die, then I'm going to do 6 is n, and p would be 1 out of 6. Okay? Here's another example. So we have a snack-sized box of Smarties, which has 10 Smarties in it. 40% of the Smarties produced are red. So what is the probability that exactly 3 of the Smarties in a given box are red? All right, we're going to use these values off to the side. The probability of getting a red Smartie is 40%, so that's 0.4. The probability of getting anything but a red Smartie would be 0.6. There are 10 Smarties in the box, so n is 10. And I want to know exactly 3. So X is 3 in this case. I just have a single probability to do. And I get an answer of 0.215, which is 21.5% chance of getting exactly 3 red Smarties. Next, what is the probability that 3 or more of the Smarties in a given box are red? Well, I can either use the direct method, adding up all the different probabilities from 3 up to 10, or I can use my indirect method, taking 1 minus the probabilities of less than 3. So here we are. The indirect method is less work, so we'll do it that way. Probability of getting 0 red Smarties is almost 0, 0.006. Probability of getting 1, probability of getting 2. We're going to subtract those from 1, so we get an 83% chance of getting at least 3 red Smarties. The expected number of red Smarties in a box, 10 Smarties in the box, 40% of them are red, so I would expect to get 4 red Smarties in a box. And finally, I can do an entire probability distribution of how many red Smarties we should get in a box. So from 0 all the way up to 10, calculating all these probabilities. And again, if I added up all these probabilities, I should get a sum of 1. And here you can see the probabilities as a probability histogram. All right, so that's your binomial probability distribution lesson. It's time to do some homework, guys. Good luck.